Hello everyone, welcome back. In this video, I'm going to talk about something called as computer system organization. If you're wondering, this being an operating systems video, why am I talking about computer system organization? Here's your answer. Usually, OS maintains and manages the hardware, isn't it? అదేగా మనం చెప్పుకుంది. So to understand how an OS works, we must first understand the hardware itself. Computer organization explains the what and how of hardware, while the operating system explains the why and when of using it. There are two different things. For the operating system to act as a bridge between hardware and software, it's very important to have a solid understanding of how different hardware components like your CPUs, registers, memory, and buses work together. So let's get going. A modern day computer system usually consists of one or more CPUs, you can see them here, and multiple device controllers. They are usually for disks, audio, graphics, etc. And also a shared bus, which is here in this particular one. This is your shared bus for communication between these different components and your main memory. So you have to understand that there are a lot of hardware components within a given system, and these usually make use of something called as device controllers. What is the main job of this device controller? Let me show you. Okay, now each of the device controller manages a specific type of device such as disk, audio, or graphics, and can control multiple devices. Now imagine if you are buying a USB hub and you connect a keyboard to it, you connect a mouse to it, you connect your pen drive to it. So that is a multiple device controller which can control multiple type of devices. Usually this diagram is taken from your textbook. You can see here is your CPU, here is your disk controller which controls the disks, and this is your shared bus through which all of these devices usually go and try to access the memory. Okay, so the device controllers typically include local buffer storage and special purpose registers to manage the data transfer between devices and their buffers. So these disk controllers typically include some kind of buffer memory, so that when you want to move information between the disk and the CPU or in something else, this buffer will be useful. Each device controller has a corresponding device driver in the operating system. You must have come across, you need to upload the drivers or drivers not found. So these device drivers are something which will enable the operating system to understand and to speak the language of these device controllers. So that is what we call as a device driver, which is something like a software. అది ఒకరితో ఒకటి మాట్లాడుకోవడానికి, అర్థం చేసుకోవడానికి, ఒక కామన్ ఇంటర్ఫేస్ ప్రొవైడ్ చేయడానికి డివైస్ డ్రైవర్స్ ని వాడతాం. So the device driver is something which understands the controller and provides a uniform interface to the rest of the operating system. So the CPU and device controllers operate in parallel. Okay, sir, panjastai. Competing for memory access. A memory controller is responsible for synchronizing the access to the shared memory among these components. So there is another memory controller here which will try to regulate the access of the memory through all these components or among all these components. You have to understand that whenever a program performs input-output operation, the device driver loads the specific registers in the device controller, and the controller reads these registers to understand what to do, such as reading a character from the keyboard and maybe movement of the mouse, etc. It then transfers data from the device to its own buffer. After it is done, after the transfer is complete, the device controller must inform the device driver that the task is done. So usually the controller sits in between the device, and it actually is responsible for transfer of information between the memory and the device itself, isn't it? Now, how do you inform that this operation is done? In this regard, we come across a term called as interrupt. So the device driver then hands control back to the operating system, providing either the data, a pointer to the data, or even a status message. Like if you want to go and read something, where is the data residing? or if you want to provide a status message like completed successfully or device not found or something like that, all these things need to be provided to the operating system. The way it is done is something called as an interrupt, a signal sent by the controller to notify the device driver that the operation is finished. Of course, interrupts is nothing like it is just like a signal. అంటే ఒక పని అయిపోయింది లేదా ఒక పని కావాలి అని చెప్పడానికి యూజ్ చేసే సిగ్నల్ ని ఇంటరప్ట్ అని పిలుస్తాము. There are many types of interrupts: hardware interrupt, software interrupt, timer interrupts, etc. So hardware can trigger any interrupt at any time by sending a signal to the CPU through the system bus. You know that the system bus is the main communication line which connects all these components together. And interrupts are essential for how hardware and operating systems interact. Now, when an interrupt occurs, ఏం జరుగుతుంది? సో ఇంటరప్ట్ వచ్చింది అంటే ఒక సిగ్నల్ వచ్చిన తర్వాత ఏం చేస్తుంది ఆపరేటింగ్ సిస్టమ్? The CPU stops what it is doing and jumps to a fixed memory location where something called as the interrupt service routine begins. So, the interrupt service routine ISR actually plays a very crucial role. This ISR is something, just a piece of code that runs automatically when an interrupt or a signal is received from hardware or software. It literally tells the operating system how to respond to the specific interrupt. అంటే ఆ ఇంటరప్ట్ ఏంటి, దాన్ని ఎలా హ్యాండిల్ చేయాలి చెప్పే లైన్స్ ఆఫ్ కోడ్ ని మనం ఇంటరప్ట్ సర్వీస్ రొటీన్ అంటాం. This routine, once it starts executing, it means that the operating system is handling the interrupt. So after handling the interrupt, the CPU resumes its previous task. అంతకుముందు ఏ పని అయితే ఆపేసి ఈ ఇంటరప్ట్ ని హ్యాండిల్ చేయడానికి CPU వచ్చిందో, once this interrupt is handled, the CPU goes back to its previous work. Okay, now let me tell you a little bit more about how this happens. So each computer has its own interrupt system, but some parts are common. The interrupt must direct the CPU to the right ISR. So ఏ ఇంటరప్ట్ వచ్చింది అనేది కనిపెట్టడం ఫస్ట్ టాస్క్. ఓకే, సో ఏ ఇంటరప్ట్ వచ్చింది అనేది కనిపెట్టిన తర్వాత ఆ ఇంటరప్ట్ కి కరెక్ట్ గా ఆ ఇంటరప్ట్ కరస్పాండింగ్ ISR దగ్గరికి సిపియుని తీసుకెళ్ళాలి. సో దట్ ఇట్ ఈస్ వెరీ ఇంపార్టెంట్ ఫర్ ద CPU to load the correct ISR for the corresponding interrupt. So a simple way to manage this is by using a generic handler that examines the interrupt and calls the appropriate routine. So ఈ హ్యాండ్లర్ ఏం చేస్తుందంటే వచ్చిన ఇంటరప్ట్ ఏది అనేది ఐడెంటిఫై చేసి దాన్ని కరస్పాండింగ్ రొటీన్ ని కాల్ చేయాలి. Because interrupts keep on happening at very routinely, they must be handled quickly as well to increase the efficiency of the system. So దీన్ని స్పీడప్ చేయడానికి what we do is a table of pointers called an interrupt vector. This interrupt vector is a pointer or even an address that tells the CPU where to find the ISR for this corresponding interrupt. అంటే వచ్చిన ఇంటరప్ట్ కి ISR అనేది ఎక్కడ ఉంది అని చెప్పేది ఇంటరప్ట్ వెక్టర్ అంటాం. సో ఇది ఒక స్పెసిఫిక్ ఇంటరప్ట్ కి ఏం లోడ్ చేయాలి, అది ఎక్కడ ఉందని చెప్తుంది. సో all these interrupt vectors are actually kept within a table. So when an interrupt occurs, a unique number, which is your interrupt vector, helps the CPU find the right address in the table and directly call the correct ISR without any extra steps. OS like Windows and Unix use this particular method. So దీన్ని అన్నిటిని ఎక్కడ ప్లేస్ చేస్తామంటే you have something called as IVT, interrupt vector table అంటాం మేము. So this interrupt vector table is a data structure stored in the memory, usually at a fixed location that holds all the interrupt vectors. And whenever an interrupt happens, based on this interrupt vector, the index laga పనిచేస్తుంది IVT కి, which works like an index to go search for in this table, which is your IVT. Okay, so in other terms, IVT is just like a lookup table. నెంబర్ చూస్తాము, ఏ ఇంటరప్ట్ అర్థం చేసుకుంటాము, ఆ ఇంటరప్ట్ ని ఎలా హ్యాండిల్ చేయాలో చెప్పేదాన్ని ఇంటరప్ట్ సర్వీస్ రొటీన్ అంటాము. ఆ ఇంటరప్ట్ సర్వీస్ రొటీన్ ని రన్ చేయాలి. ఓకే, నౌ ది ఇంటరప్ట్ సిస్టమ్ ఆల్సో needs to save the CPU state. ఎప్పుడైతే CPU might be busy, CPU might be working on something else. If an interrupt happens, then the CPU state should be saved. This is, we usually call it as context switching in some cases. So it can continue. ఎందుకు save state చేయాలి? Because after servicing this interrupt, the CPU should go back to wherever, whatever it is doing and continue that particular work. If the ISR needs to change the processor state, it must save the current state first. అంటే జరుగుతున్న దాన్ని ఆపి దాన్ని సేవ్ చేయాలి. And interrupt అయిపోయిన తర్వాత then restore it after the interrupt is handled. When the interrupt is done, the CPU uses the saved return address to resume its previous work as if the interrupt never happened. In simpler terms, the CPU might be busy doing some kind of work, and an interrupt is actually signaled by hardware or software. So when this happens, the CPU has to stop its current execution, save the state of the current execution, and then move on to the correct ISR, load it, execute it. That means the interrupt is handled, and then go back to its previous work. This is how the interrupts must be handled. I'll show you a diagram for better understanding. Now, the basic interrupt mechanism allows the CPU to respond to asynchronous events, like a device needing service. The CPU checks a wire called the interrupt request line, IRL. This is called as IRL after every instruction. Generally, IRL is assigned to one device. So that means each device will have its own IRL, and the CPU keeps checking these IRLs. In other ways, IRL or an interrupt coming through IRL is someone just raising their hand saying that I need a service. Now, if a device signals an interrupt, the CPU reads the interrupt number, that is your interrupt vector, looks it up in the interrupt vector, and jumps to the correct interrupt handler. అంటే CPU ఆ ఇంటరప్ట్ వెక్టర్ నెంబర్ని రీడ్ చేసి తర్వాత ఇంటరప్ట్ వెక్టర్ టేబుల్లోకి వెళ్ళి ఆ టేబుల్లో ఆ ఇంటరప్ట్ నెంబర్ పక్కన ఉన్న లొకేషన్ని బట్టి దాని కరెక్ట్ ఐఎస్ఆర్ని కాల్ఫర్ చేస్తుంది. ది హ్యాండ్లర్ సేవ్స్ ద CPU స్టేట్, determines the cause, services the device, restores the state, and returns to the interrupted program. So ఇది చూస్తే CPU ఇక్కడ ఉంది. So device driver initiates IO, fine. Then the next step is initiates IO, interrupt ready, output complete or error generates interrupt signal. So ఎక్కడైతే interrupt signal వచ్చిందో ఇక్కడ ఇదంతా జరిగే ముందు CPU is executing checks for interrupts between instructions, and ఎప్పుడైతే interrupt అనేది జనరేట్ అయిందో the CPU will check it out, and it automatically passes the control to the interrupt handler, which processes the data, then returns from the interrupt, and the CPU resumes processing of the interrupt task. So 1, 2, 3, 4, 5, 6, and finally the 7, where it keeps on happening. This is how a CPU usually handles interrupts. Now, this is a basic system which has got some limitations, and as I told you, there are numerous interrupts which happen in the system at a regular basis. So how do you speed up this process? How can you implement this process to happen in a much more efficient manner? There are three different features that are added. The first one being, why don't we defer the interrupts during critical processing? So critical processing జరిగేటప్పుడు unnecessary interrupts లేదా low priority interrupts ని ఆపడం ఎట్లా? Second one is efficiently dispatching to the correct interrupt handler. As soon as an interrupt happens, we need to go and check for it and load the appropriate interrupt service routine at a faster pace. ఎంత త్వరగా చేయగలిగితే అంత మంచిది. The last thing is multi-level interrupts to prioritize urgent requests, assigning priorities to the interrupts. For the first feature, what we do is, most of the CPUs have two interrupt lines. The first one is something called as a non-maskable interrupt. You can see here, a non-maskable interrupt for critical issues like hardware errors. Well, that means if this happens, the CPU has to stop it, whatever it is doing, and go and service it. A maskable interrupt for regular device requests, which can be turned off during critical sections. And the CPU అనేది ఏమైనా critical గా పనిచేస్తున్నప్పుడు only it will react to interrupts coming through this particular line only. And ఈ maskable interrupt line లో వచ్చి defer చేయొచ్చు. That means I can do it at a later point of time. This is the first feature. The second one being, vectored interrupts help quickly find the right handler. But there may be more devices than vector slots. అంటే more devices ఉండొచ్చు. ఇందాక మనం అనుకున్నాం కదా అలానే. So for this particular purpose, what they are doing is, there is a concept called as interrupt chaining. Interrupt chaining ante each entry in the vector table points to a head of the list of handlers. Now this is actually taken from Bell and John T. IO systems. You can see these are all the Intel's interrupt types. You can see the vector number here and you can see the description. Now, when an interrupt occurs, the system checks handlers in the list until it finds the one that can handle the request. So here what you do is, rather than having one particular pointer to point to one ISR, you can group different ISRs together to one vector, so that if one vector happens or if an interrupt happens, you check that vector and you then keep checking the devices which are linked together under that particular vector till you find the right device and then service it. So this approach balances the speed and efficiency without needing a huge table or a single slow handler. So okay, table loads of vectors numbers పెట్టుకునే బదులు చైనింగ్ ద్వారా టేబుల్ సైజ్ తగ్గుతుంది, lookup time తగ్గుతుంది. And the third feature that we discussed is interrupts are organized into interrupt priority levels. This allows the CPU to handle urgent interrupts first and defer lower priority ones without blocking all interrupts. That means if you can categorize which interrupt is of high priority, which interrupt is of low priority, and you only block the CPU in case if a high priority interrupt comes in. And other than that, if there is a low priority, we can make the CPU to access it or to service it at a later stage. Interrupts are quite essential in modern operating systems for handling asynchronous events, such as signals from device controllers or hardware faults, etc. There are many things which will lead to an interrupt. So to prioritize the urgent tasks, system use interrupt priority levels. Since interrupts are crucial for time-sensitive operations, handling them efficiently is key to maintaining strong system performance. So all these things have to be carefully designed and thought of when you want to implement a system that is quite efficient. Okay, now let's move on to the next concept, which is very important and which we come across every day, is your storage management. The CPU can only load instructions from the memory. That means the CPU can only talk to your main memory. And that is the reason all the programs that need to be executed are loaded into your main memory first. Main memory, usually we call it as RAM or random access memory, is a place where the programs which are to be executed are placed first, such that they can be allocated the CPU next. Now RAM is fast, rewritable, and usually built using dynamic random access memory technology. But the flip side is it is volatile, and power pote dantlo contents store cheyadu. Its contents are lost when the power is off. For critical programs like the bootstrap program, ఈ bootstrap program అనేది first system అనగానే run అయ్యే first program. What it does is it actually identifies where your operating system or the kernel is located, and then its duty is to load the kernel into the RAM, pass the control to the kernel. That is the duty of the bootstrap program, which is the first program which usually runs when you power on your computer. So which starts the operating system. We use non-volatile memory. For this particular programs to be stored, we use something called as EEPROM, electrically erasable programmable read-only memory, or in some cases we call it as firmware. So EEPROM is slower, can't be written often, but it is permanent and is used for static data like the serial numbers. There are many types of memory that are used in computers, and we will discuss it slowly. So all types of memory store data as an array of bytes, each with its own address. We will study more about memory management later on. So memory management అనేది separate concept ఉంది. So ఆ concept దీని గురించి we will discuss in depth. So the CPU uses two instructions mainly. The first one is something called as load instruction antamu, which is used to read data from memory into the registers, and store instructions to write data back to the memory. So next slide I'll explain more about these two instructions. And the CPU also automatically fetches instructions from memory based on the program counter. This program counter is a value which tells the CPU to fetch what is the next instruction to be fetched for this particular program. So program lo next a instruction execute cheyali అనేది చెప్పేది program counter. So this always points out to the memory location where the next instruction is currently residing. So the CPU can go there and get that particular instruction and execute it. ఇది బెటర్గా అర్థం కావాలి అంటే మనకి కొంత బేసిక్స్ తెలుసుకోవాలి. సో ద బేసిక్ యూనిట్ ఆఫ్ a computer storage is bit. Bit actually stands for binary digit. It can either have only two values. These are either 0 or 1. All other storage in the computer is based on collection of bits. So we start with the first basic collection, which is byte, which is nothing but 8 bits. So a byte and 8 bits. Next forms kilobyte, which is KB. These are your abbreviations, how we denote them. And please do not get confused with BPS. Network speed ni BPS to measure chestam. These are bits per second, small b. Lower case b rastam, like MBPS ani, లేకపోతే KBPS అని లేదా GBPS అని ఇలా రాస్తాను. సో దీస్ ఆర్ యువర్ బిట్స్ పర్ సెకండ్ విచ్ ఈస్ ఫర్ which is your network speed. But here this is storage. We always mention it in bytes. So kilobyte, megabyte, you can see these are your numbers, and this is usually roughly what we approximate it to. So gigabyte, terabyte, TB, petabyte, exabyte, zettabyte, yottabyte, YB. Okay, so these are all how you usually measure the memory in case of a computer system. Okay, now once we know this, it becomes easier when we start reading the other components. Now, as I told you, I will be discussing about load and store instructions. This is a typical instruction execution cycle in a von Neumann system. What happens is, first the CPU start with the fetch. It fetches an instruction from the memory. This is your main memory. You can see RAM here. This is your main memory. The instructions are being fetched from the RAM, and then they are decoded. So decode the instruction, and in order to execute that, if you need any other data, you need to fetch them again from the RAM, any data to execute that particular instruction, and then finally execute that. And after execution, if required, you again place those operands and the results into the RAM, into the memory. So fetch, decode, execute, store. This is commonly how the instruction execution cycle goes on. These are the different steps that are involved. The memory itself just sees a stream of addresses. As I told you, all the memory, we usually denote them as a series of bytes, each byte having its own address. So it doesn't know if there are for instructions or data. So what we want to do, as I told you, that any program that wants to be executed must be placed in the main memory, so such that the CPU can go fetch it and execute it. But the problem is, your RAM or your main memory is not large enough to hold all the programs. It is too small for everything, and it is also very expensive, and it is volatile and loses the data when powered off. So that is the reason we have other storages as well within your computer. So the computers use secondary storage like your hard drives or non-volatile memory to store large amounts of data permanently. Non-volatile means even though the power is gone, the memory contents are intact. So programs and data are loaded from secondary storage into the main memory when required. Secondary storage is slower than RAM, so efficient storage management is essential. That is why I said there are separate topics on memory management. How do you maintain all these things? How can you do it efficiently? There are also other storage types. This is called as tertiary storage, which is like a backup or a Blu-ray, which is slower and used for special purposes to archive data that no longer needs to be accessed regularly. That means if you want to store something, if you want to keep the data aside, then you go for tertiary storage. And the next one is something called as cache memory, which is faster and smaller, and is typically used for frequently accessed data. Now, in order to organize these different types of memory that are used, we usually draw this storage device hierarchy diagram. These are all which are maintained in one particular order. If you see here, the top one, the uppermost one is a register. This is the smallest in size and the most fast one and most expensive one. Okay, so this is how you write it down. Next, after registers, we get the cache memory. So after cache memory is the main memory. You have to understand that the CPU can only read instructions and contact or interact directly with these three components only. So registers, cache memory, and main memory. And these three are volatile in nature. That's what we have written, volatile in nature. And these three are the smallest components also with regards to the storage capacity as well. And from if we move on, we come to the secondary storage area, which the most commonly used secondary storage are your SSDs, which is your solid state disk, and HDD. This is your hard disk, and SSD, solid state disk. These both are non-volatile and commonly used as secondary storage in your computers. And then if we move to tertiary storage, we get optical disk, which is your CDs, DVDs, Blu-rays, etc. And finally, we also have magnetic tapes as well. So these can contain large amounts of data. So all the storage systems share the basic functions of storing and retrieving the data, but they differ in speed. These are the fast, as I told you, speed, size, and volatility. If you can see, these are the three components which are volatile in nature, and all the rest of the components are non-volatile. That means they do not lose the data even in case of a power loss. So power poina వీటిలో data పోదు, అందుకని వీటిని non-volatile storage అంటాము. Now, the commonly used secondary storage devices are your hard disk devices and non-volatile NVMe devices like flash memory. These storage types hold both programs and data which are loaded into memory as required. అవసరాన్ని బట్టి దీంట్లో ఉన్న programs ని మనం మెమరీలోకి లోడ్ చేస్తాము. So a typical computer storage system includes registers, main memory, and secondary storage such as your HDDs or NVMs. So volatile storage ante RAM kanindi, cache loses its content when power is off, while non-volatile storage keeps data intact and is the main focus for programs and data storage. జనరల్ గా కంప్యూటర్ భాషలో చెప్పాలంటే స్టోరేజ్ మనం వాడేది నాన్ వాలటైల్ యూజ్ చేయాలి, బికాస్ యూ కెన్ కీప్ డేటా పర్మనెంట్లీ ఇన్ యువర్ కంప్యూటర్. అండ్ వెరాజ్ నాన్ వాలటైల్ స్టోరేజ్ కెన్ బి మెకానికల్ లైక్ HDDs, optical disks, or tapes which are larger, slower, and cheaper per byte, or even electrical things like flash memory, FRAM, and SSDs which are faster, smaller, and a little bit more expensive when you compare to the mechanical ones. But you have to understand that we got loads of different types of memories available. And semiconductor memory used in higher levels of storage such as registers and cache is built from electronic circuits. Flash memory, a popular NVMe type, is used widely in your smartphones. మనం రోజు వాడే phones లో వాటిలో ఉండే మెమరీని ఫ్లాష్ మెమరీ అంటాము. That is also a non-volatile memory type only. So smartphones లో కానివ్వండి, tabs లో కానివ్వండి, laptops, desktops, and even in case servers, flash memory is becoming more and more popular option nowadays. In summary, efficient storage management is vital for system performance, and different types of storage are used depending on the system's need for speed, capacity, durability. మనం వాడుకునే సిస్టమ్ ని బట్టి మనం ఇందులో ఏ టైప్ ఆఫ్ మెమరీని ఇంప్లిమెంట్ చేస్తాం అనేది డెసిషన్ తీసుకుంటాం. ఓకే, సో విచ్ బ్రింగ్స్ us to the last topic for our particular discussion, which is your IO structure. As you know, IO management is also a crucial task for the operating system. మనకి ఈ హార్డ్వేర్ కాంపోనెంట్స్ లో ఇన్పుట్ అవుట్పుట్ forms a major role. So a large part of the operating system is focused on managing input output devices because they are critical for system performance and reliability, and they vary widely. Ani oka rakamga unnavu, different IO devices are present. So in a general computer system, devices share a common bus to exchange data. Intak manam chubincham kada. So there are a lot of hardware devices and all of them are connected via the shared bus, and this bus also gives them a common access to the memory. So for small data transfers, interrupt driven IO works well. ఇందాక మనం అనుకున్నట్టుగా డివైస్ కంట్రోలర్ కనుక డేటా మూవ్ చేయదలుచుకుంటే ఇంటరప్ట్ రైజ్ చేస్తుంది. ఇంటరప్ట్ రైజ్ చేసినప్పుడు CPU చేస్తున్న పని ఆపి ఆ ఇంటరప్ట్ ని హ్యాండిల్ చేసి ఓకే చేస్తుంది. బట్ ఇట్ బికమ్స్ ఇన్ఎఫిషియంట్ ఫర్ లార్జ్ డేటా ట్రాన్స్ఫర్స్ లైక్ దోస్ ఇన్ ది నాన్ వాలటైల్ స్టోరేజ్. అంటే చిన్న మెమరీ సెగ్మెంట్స్ ని మూవ్ చేయడానికి interrupt driven IO is good enough, but if you want to move large amounts of data from your non-volatile storage back and forth, then this becomes a problem. అందుకని ఏం చేస్తున్నారంటే we use a concept called as direct memory access, DMA. So ఇదేం చేస్తుందంటే once you set up the necessary buffers and counters, the device controller transfers the entire blocks of data directly between the device and memory, freeing the CPU to do other tasks. అంటే ప్రతి బయటికి నేను ఇంటరప్ట్ రైజ్ చేసి CPU నాపి CPU చెప్పడం కాకుండా, rather than doing lot of interrupts, I will only raise an interrupt after completing a full block of data transfer. So instead of multiple interrupts for each byte, DMA uses one interrupt per block to notify the CPU when the transfer is complete. Some high-end systems use a switch architecture instead of a shared bus, allowing multiple devices to communicate simultaneously. Ante okate kakunda switch architecture means they can communicate simultaneously at the same time. In such systems, DMA is even more effective. You have to understand that DMA is most useful nowadays because of the modern day systems that we are using. It allows devices to transfer data directly to and fro without actually disturbing the CPU in every step of the data transfer. ప్రతి దానికి CPU డిస్టర్బ్ చేయకుండా maximum amounts of data మనం మూవ్ చేయొచ్చు. This leads to faster, more efficient system performance. These are all some of the critical components which come under the computer system organization. As I told you earlier, in order to study OS well, you have to understand the aspects of hardware also. We have come to the close of this video, and in the next video, we will discuss more about the operations of OS. Till then, take care.